Right now, as you're watching this, there's a volcano inside the United States that has been erupting continuously for more than 5 years. Not steaming, not rumbling, erupting. Molten rock reaching the surface every single day since the summer of 2021. It is not Kilauea, it is not Mount St. Helens, it is not Yellowstone, and it is not the volcano that had Anchorage checking its phone every morning in the spring of 2025. It is a 709-foot mountain on an uninhabited island in the central Aleutians, roughly 200 miles southwest of Anchorage, and its name is Great Sitkin. The United States Geological Survey has held it at Volcano Alert Level Watch and Aviation Color Code Orange without a single break since July of 2021. 5 years at Orange, 5 years at Watch. And running directly over the top of it are some of the busiest air corridors on the planet. So here is the question. This whole video is built around how does an American volcano erupt for 5 straight years and almost nobody notices? Before we go any further, let me tell you exactly what this video is and what it is not. No guessing, no dramatizing. Just the facts pulled from Alaska Volcano Observatory bulletins, from peer-reviewed papers and Geophysical Research Letters, and the Journal of Volcanology and Geothermal Research, and from United States Geological Survey publications. Where scientists are uncertain, I will tell you they are uncertain. Where a number is an estimate, I will call it an estimate. Here's my question for you, and I genuinely want to see your answers in the comments. Had you ever heard of Great Sitkin before clicking on this video? Yes or no, just that. I'm curious how many of you knew there was a 5-year eruption going on in your own country. If you find this useful, subscribe to the channel. It is completely free, it takes 1 second, and it is the single biggest thing that helps this work continue. Hit the thumbs up while you're there. Let's push for 5,000 likes on this one. Thank you, seriously, for being here. Now let's get into it. The story starts earlier than most people think, not in 2021, in 2016, in a 2024 paper published in the Journal of Volcanology and Geothermal Research. John Power of the United States Geological Survey and Diana Roman of the Carnegie Institution for Science went back through 24 years of seismic records at Great Sitkin from 1999 through 2023 and classified every event they could find. What they identified was a set of precursors that began in July of 2016. Deep, long-period earthquakes and volcano-tectonic earthquakes at mid-crustal depths. In plain language, rock cracking and fluid moving several miles underground in a pattern that suggested new magma had intruded from below. That deep signal was almost immediately followed by shallow activity. Long-period events and small earthquakes in the upper crust. Power and Roman concluded there was a strong linkage between the deep and shallow parts of the system, and that the shallow portion was likely capped, sealed shut, by an old lava dome left behind from an eruption in 1974. Think about that for a second. 5 years of pressure quietly building underneath a plug of solid rock, and almost no one outside a small circle of Alaskan seismologists was paying attention. The seal broke on May 25, 2021. A single explosion at the summit sent an ash cloud up to roughly 15,000 feet. For a volcano that had produced only one ash explosion since 1974, that was a genuine event, and it made the news for about a day. Then it went quiet again, and the world moved on. The world moved on too early. In mid-July of 2021, satellite imagery started showing elevated surface temperatures in the summit crater. A lava dome was growing. By the first week of August, using a satellite image taken on August 3rd, scientists measured that dome at about 180 meters across, roughly 590 feet, with an estimated volume of about 1 million cubic meters. On the morning of August 5th, observers on Adak Island, about 26 miles to the west, reported what looked like low-level lava fountaining from the vent. The Alaska Volcano Observatory measured the effusion rate, which is simply how fast lava is coming out. In August 2021, it ran between 3 and 7 cubic meters per second. By September, it had dropped to around 2. By November, it was below 1 cubic meter per second. And this is the part that matters. It never stopped. By the end of that first year, the lava field covered 1.3 square kilometers, about half a square mile, with an estimated total volume of 0.031 cubic kilometers. The dome inside the summit crater had grown to roughly 1,230 meters wide, east to west. 3 separate flow lobes had pushed out of the crater and down the flanks. The west lobe ran about 830 meters. The south lobe about 865 meters. The north lobe about 180 meters. In that same year, Avio located 966 earthquakes near the volcano, ranging from magnitude -1.1 up to 2.1, at depths from above sea level down to about 32 kilometers. Most of them clustered in the top 10 kilometers of crust directly beneath the edifice. That is not a volcano taking a breath. That is a volcano with the tap open. And then it kept going, through 2022, through 2023, through 2024, Every year the flow direction shifted as different parts of the underground system took over, north, then east, then south, then northeast, with each new lobe burying the one before it. In July of 2024, AVO reported satellite radar showing the active flow growing to the east and south, overtopping older lava erupted between 2022 and 2024, with blocks of rock breaking off the steep flow margins and registering in the seismic data as rock falls. By October of 2025, satellite radar was tracking a flow front advancing roughly 15 to 20 meters per week. That is about the length of a school bus every 7 days, slow enough that you could outwalk it wearing sandals, relentless enough that after 5 years it has buried the 1974 dome almost entirely and filled most of a crater that is about a mile across. Here is where it stands as of this recording. On February 20th, 2026, AVO reported continued slow dome growth near the vent, elevated surface temperatures whenever the clouds broke, and low seismicity with occasional small earthquakes and rockfall signals. On March 13th, the same picture, with minor dome growth to the southwest. Through the spring, the same. On August 7th, 2026, the weekly update noted something worth pausing on. A GNSS sensor on the northwest shore of the island is recording deflation. The ground is sinking, consistent with pressure being released at depth because lava is coming out at the summit. Satellite data showed the dome gradually expanding toward the east-southeast. And on August 13th, 2026, the daily bulletin said what it has said in some form for 5 years. Slow eruption of lava within the summit crater continues. Now, the human scale. Great Sitkin Island is uninhabited. The nearest community is Adak, 26 miles west, the southernmost city in Alaska. It sits on what used to be a naval air station that closed in 1997. At its Cold War peak, roughly 6,000 people lived there. The 2020 census counted 171. More recent Census Bureau survey estimates put it in the 70s. That is the population within eyesight of a 5-year eruption. Which brings us to the actual reason this matters. And it has nothing to do with the people below and everything to do with the people above. To understand why anyone should care about a lava dome on an empty island, you have to go back to a December afternoon in 1989, about 1,300 miles east of Great Sitkin. On December 15, 1989, KLM Flight 867 was descending toward Anchorage. It was a Boeing 747-400, registration PHBFC, less than 6 months old, flying from Amsterdam to Tokyo with a refueling stop in Alaska. On board were 231 passengers and 14 crew. About 150 miles away, Redoubt Volcano had begun erupting roughly 10 hours earlier. At around 25,000 feet, the aircraft entered what looked like an ordinary dark cloud. It was not. It was volcanic ash. Sulfur-smelling smoke filled the cockpit. The crew pulled on oxygen masks and powered up to climb out of it, which, tragically, was exactly the wrong instinct, though nobody knew that at the time. Within roughly 20 seconds, all 4 General Electric CF680C2 engines flamed out, one after another. A 747 with no engines is a glider. This one fell from 27,900 feet to 13,300 feet, more than 2 miles, over the Talkeetna Mountains, which rise to 11,000 feet. Passengers later described a steep, silent descent, screaming, people being sick, near panic in the cabin. The crew got all 4 engines relit and landed safely at Anchorage. Nobody was injured, not one person. According to United States Geological Survey publications, the damage to engines, avionics, and airframe came to about $80 million, including the replacement of all 4 engines. The windscreen, sandblasted by ash at more than 500 miles an hour, ended up on permanent display in Anchorage as a teaching tool. During that 1989 to 1990 eruption sequence at Redoubt, more than 20 aircraft were damaged, most of them flying more than 600 miles from the volcano. Between December and February, 5 commercial jetliners took ash damage. Now compare the 2 stories, because the contrast is the whole point. Redoubt in 1989 was loud, explosive, close to a major city, and it nearly killed 245 people in a single afternoon. It generated headlines around the world. Great Sitkin has been erupting for 5 years, and most Americans have never heard the name. But here is what makes the comparison genuinely useful rather than just dramatic. Redoubt is also a preparedness story, and a good one. Congress funded Alaska volcano monitoring in the fiscal year 1988 appropriations. The Alaska Volcano Observatory was established that year. AVO installed seismic instruments on Redoubt, and that network became operational in October 1989, just weeks before the volcano erupted. According to the USGS, those instruments recorded a series of earthquakes beneath the summit beginning about 24 hours before the first major eruption on December 14th, and they provided the only dedicated, continuous information about the size and extent of the activity that followed. That warning let authorities take protective action. Weeks. The network went live weeks before it was needed. That is not a scary story. That is a story about a decision made by people in a budget meeting that paid off almost immediately. And the reason Great Sitkin sits at Aviation Color Code Orange today, with bulletins issued daily, is the direct institutional descendant of that decision. Because the sky above the Aleutians is not empty. According to the USGS, North Pacific and Russian Far East air routes pass over or near more than 100 potentially active volcanoes, and those routes carry more than 50,000 passengers and millions of dollars of cargo every day between Asia, North America, and Europe. An older USGS fact sheet notes that along these routes, at least 15 aircraft were damaged by volcanic ash between 1980 and the late 90s, with about 80 such encounters worldwide in the same period, causing hundreds of millions of dollars in damage and lost revenue. No fatalities, not one. But the USGS itself flagged the obvious risk in that same document. Air traffic over volcanically active regions keeps growing, and that growth increases the odds of a deadly encounter. So a volcano nobody lives near is still a volcano tens of thousands of people fly over. That is case A and case B. Now, here's where it gets more interesting scientifically, because for the first couple of years, the people studying Great Sitkin could not fully explain why it would not stop. The answer, or at least the leading answer, came in June 2023 in Geophysical Research Letters. A team led by Dr. Xiaotao Yang of Purdue University's Department of Earth, Atmospheric, and Planetary Sciences, working with Diana Roman of Carnegie Science, Matthew Haney of the USGS, and Cody Kupres, used a technique called full-wave ambient noise tomography. Here is what that means without the jargon. The Earth is always humming. Ocean waves hitting coastlines, wind, distant traffic, all of it puts a constant low-level vibration through the crust. If you have enough seismometers listening, you can treat that background hum as your light source and effectively take a CT scan of the rock underneath. Where seismic waves slow down, the rock is softer, hotter, or partly molten. Yang's team imaged the upper 6 kilometers of crust beneath Great Sitkin using avio data collected between 2019 and 2020, before the eruption started. They found 2 distinct low-velocity anomalies. Not one magma chamber. 2. One to the northwest of the summit crater, below 3 kilometers depth. One to the southeast, at 2 to 4 kilometers. Each with a bulk melt fraction estimated at roughly 2.5 to 9%, meaning mostly crystal mush, with a small fraction of actual liquid rock threaded through it. From that, they proposed a 6-stage eruption cycle in which the 2 reservoirs alternate, recharging on different schedules and feeding the surface at different times. That model does something useful. It explains why the earthquakes had been migrating back and forth across the island for years, and it offers a mechanism for an eruption that keeps handing itself off rather than running dry. As Dr. Yang put it when the study was published, the unpredictability of volcanic activity can be societally disastrous. That is the whole reason for the work. Then came the follow-up. In August 2024, again in Geophysical Research Letters, Cody Kupres, Yang, Haney, and Roman published a study measuring seismic velocity changes at Great Sitkin from July 2019 through July 2023, using ambient noise interferometry at 5 3-component seismic stations. They found prominent, spatially variable increases in seismic velocity during the lava effusions. The rock underneath was getting seismically faster as magma left. Their interpretation is that erupting magma is physically modifying the structure of the volcanic system, and that this change may persist for a long time, possibly until the next cycle begins with effusion stopping, recharge resuming, and the ground starting to inflate again. And that team said something else that I want to be honest about, because it cuts against the tidy version of this story. They wrote that a denser deployment of seismometers at Great Sitkin would provide higher resolution data and let them distinguish between competing explanations. In other words, we have a good hypothesis, and we do not have enough instruments on that island to confirm it, which brings us to the escalation that genuinely concerns me, and it is not the lava, it is the monitoring. In early 2023, according to AVO's own eruption summary, the data streams from every instrument on Great Sitkin went down because of weather on January 2nd, and the outage lasted until January 28th, nearly 4 weeks with the on-island network dark during an active eruption. AVO tracked the volcano through satellite data and regional infrasound instead. That worked. But it worked because there were backups, and because someone was paying attention. That backdrop is not new. Back in 2013, during federal sequestration, John Power, then the USGS scientist in charge at AVO, told reporters that budget cuts had forced the observatory to shut down real-time monitoring at 5 volcanoes, and to abandon a plan to install seismic monitors at Cleveland Volcano in the Aleutians, which was erupting at the time. His words were direct. Because the budget had been declining for so long, they had no hope of addressing the Cleveland eruption the way it really should be addressed. A 2015 USGS release gives you the shape of the problem. At that point, Avio operated 216 seismic stations covering 29 volcanoes, and 176 of them were operational. Deferred maintenance had left Wrangell and Four-Peaked inoperable, and Veniaminof running on 3 of 9 stations. Repairs had just been completed at Aniak Chak, Gariloy, Tanaga, Westdahl, and Shishalden. As Power said at the time, restoring those systems greatly improved Avio's ability to track unrest and issue advance warnings, and he noted these volcanoes pose significant hazards to local and international air traffic, the fishing industry, municipalities, businesses, and the general public. Access, as Avio puts it plainly, is logistically challenging. That is the polite phrase for a 1,000-mile flight to an island with no runway, in weather that closes for weeks, and the pressure has not gone away. In 2025, it was reported that the Alaska Earthquake Center would lose a NOAA grant of about $300,000 a year that funded seismic stations feeding tsunami warnings, with a renewal request through 2028 denied. Center Director Mike West noted the loss would include a handful of sites out in the Aleutians and the Bering that had been there for decades specifically for that purpose, with no substitute stations surrounding them. To be precise, because precision matters here, those are earthquake and tsunami stations, not volcano stations, and they are run by a different institution than Avio. I am not going to tell you the volcano network is being switched off, because that is not what the reporting says. What I am telling you is that the same remote, expensive, hard-to-reach infrastructure that watches the Aleutians is under sustained financial strain, and Great Sitkin sits in the middle of it. Now let's deal with the panic takes, because there are a few, and they are all wrong in interesting ways. The first one you will see in comment sections: 5 years of eruption means pressure is building for something catastrophic. The data says the opposite, that GNSS sensor on the northwest shore of the island is recording deflation, not inflation. The ground is going down, which is what you expect when magma is leaving storage and reaching the surface. A volcano that erupts continuously is a volcano that is venting, not bottling. There have been no explosions at Great Sitkin since May 2021. Seismicity has stayed low for years, with most of the recorded signals being small rockfalls off the growing dome. If Great Sitkin were building toward a large explosive event, the signature would be different. Rising earthquake rates, surface inflation, stronger gas emissions. That is exactly what Alaskans watched at Mount Spur in early 2025, and I will come back to that in a moment. The second take: a 5-year eruption is bizarre and unprecedented. It is not. It is unusual for the Aleutians, and it is by far the longest effusive eruption in Great Sitkin's modern record. But globally, long-lived effusive eruptions are a well-documented category. Kilauea's Puu vent on Hawaii Island erupted more or less continuously from January 1983 to April 2018. That is 35 years. Santiaguito in Guatemala has been growing lava domes since 1922. Stromboli in Italy has been in near-constant activity for millennia, which is why sailors called it the lighthouse of the Mediterranean. Slow, sustained lava output is not an anomaly. It is one of the normal modes a volcano can settle into. The third take, and this one I hear constantly on every volcano video, is this connected to the other volcanoes acting up? Is the ring of fire waking up? Here I want to be careful, and here is an important bit of context. Volcanoes along the same subduction zone share a common driver, which is the same plate boundary supplying them with magma over geological time. That is real. What is not supported is the idea that an eruption in one place triggers an eruption 1,000 miles away on human timescales. Great Sitkin's own record shows precursors going back to 2016, 5 full years before the surface broke. Its plumbing, as Yang's team imaged it, is local, specific, and it has its own recharge history. It is not taking orders from Iceland or Indonesia. And the fourth one, if it were dangerous, we would have heard about it. That is the assumption I would push back on hardest and gently, because it is the reason for this whole video. Great Sitkin is at Aviation Color Code Orange. Orange is the third of 4 levels. It means an eruption is underway with limited or no ash emission. It has been there for 5 years. The reason you have not heard about it is not that scientists downgraded the risk. It is that nothing photogenic has happened, and news coverage tracks images and casualties, not alert levels. Contrast that with Mount Spur. In March 2025, Avio reported elevated seismicity, ground deformation, and about 440 to 450 metric tons per day of sulfur dioxide measured during a March 7th overflight, up from under 50 tons per day in December 2024. The Municipality of Anchorage Emergency Operations Center raised its activation level. Anchorage stores sold out of masks. Schools published preparedness pages. Then the intrusion stalled. By June 2025, Avio reported ground deformation had stopped, and the likelihood of eruption had declined. On August 20th, 2025, Spur was lowered to green and normal. Spur never erupted and got months of coverage because it is 80 miles from 300,000 people. Great Sitkin has been erupting the entire time and got almost none because it is 26 miles from about 70. Neither of those outcomes is a scientific judgment. They are both a function of where the cameras are. So let's talk about the actual mechanism, because once you understand it, the whole 5-year thing stops feeling mysterious. The Aleutian Arc exists because the Pacific Plate is diving beneath the North American Plate along the Aleutian Trench. As that slab sinks, it heats up and releases water locked in its minerals. That water rises into the mantle, wedge above, and does something counterintuitive. It lowers the melting point of the rock it enters. Rock that would otherwise stay solid begins to melt. That melt is buoyant, so it rises, collecting in reservoirs in the crust. Great Sitkin and erupts basaltic andesite. That composition is the key to everything you have just heard. Silica content controls viscosity, and viscosity controls whether a volcano explodes or oozes. High silica magma like rhyolite is thick, traps gas, and builds pressure until it fails catastrophically. Low silica basalt is runny and lets gas escape easily, which is why Hawaiian eruptions produce fountains and rivers rather than Plinian columns. Basaltic andesite sits in between, thick enough to pile into a dome rather than run to the sea, fluid enough that gas can bleed off instead of accumulating. Add the two reservoir structure Yang's team imaged with different recharge histories feeding the surface in alternation, and you get exactly what the satellite record shows. A slow, stubborn, unspectacular extrusion that shifts direction every year or so and simply does not run out. The 1974 dome is instructive here. That eruption was explosive, rated VI2, and it produced at least one ash cloud that likely exceeded 25,000 feet. It also left a steep-sided lava dome in the crater, and that dome then sat there for decades acting as a lid. A poorly documented eruption in 1945 had done something similar, producing a dome that 1974 partly destroyed. So the pattern at this volcano is build a plug, hold pressure, break the plug, build a new one. The current eruption is the plug building phase, and it has now buried the 1974 dome almost completely. As for why ash is the specific danger to aircraft rather than lava, volcanic ash is not soft. It is pulverized rock and volcanic glass, sharp and abrasive. Jet engines run their combustion sections hotter than the melting point of that glass. Ash gets ingested, melts, then resolidifies on cooler turbine components, choking airflow and stalling the compressor. That is precisely what happened to KLM 867. It is also why radar does not save you. Weather radar is designed to detect water droplets. A dry ash cloud can look like ordinary cloud, or like nothing at all, right up until the engines quit. That is why the aviation color code exists as a separate scale from the ground alert level, and why an uninhabited island rates a daily bulletin. So what do you actually do with this? Here's the practical part, and I am going to keep it specific to this hazard rather than giving you generic prep advice. If you fly the Pacific, particularly Asia to North America routes, know that dispatchers and the Volcanic Ash Advisory Centers route around ash and are good at it. There is no consumer action item here beyond understanding why your flight occasionally takes a long, strange detour over the North Pacific. When that happens, that is the system working. It has cost airlines a great deal of money and it has saved lives. If you live in Alaska or anywhere downwind of an active arc, get the alerts at the source rather than from social media. AVO publishes daily and weekly updates and issues volcano observatory notices to aviation directly through the USGS hazard notification system. Note that beginning in early March 2026, the USGS moved to an updated VONA format. So if you have an old bookmark or a script scraping the feed, check it. Build an ashfall kit, and understand it is not a dust kit. Get N95 rated respirators, not cloth masks. Get sealed eye protection because ash abrades corneas. Store water because ash contaminates open supplies and clogs filtration. Protect the machines. Ash destroys engines, and that includes your car. If ashfall starts, do not drive unless you must, and do not run your windshield wipers on a dry, ash-covered windscreen, because you will grind the glass. Wash it off with plenty of water first. Change vehicle air filters afterward. Seal computers and electronics in plastic bags before ash arrives, not after. Think about roofs. Volcanic ash weighs far more than snow of the same depth, and it gets dramatically heavier when it rains. Clearing accumulated ash off a roof is a real structural concern, and it is also the moment people get hurt, so plan for it before it is on there. Stay indoors during active fall, close windows and vents, and keep pets in. Once it settles, dampen ash lightly before sweeping so you're not resuspending it into your lungs. And if you want to do something that actually changes outcomes, pay attention to how volcano monitoring gets funded in your state and country. Redoubt in 1989 is the case study. That network went live weeks before it was needed, and it worked because someone funded it before there was a headline demanding it. Here is the honest summary. Great Sitkin Volcano in the central Aleutian Islands has been erupting lava continuously since July 2021, following a single explosion in May of that year. It has been at Volcano Alert Level Watch and Aviation Color Code Orange for 5 years without interruption. Its lava has filled most of a summit crater roughly a mile across, buried the dome left by the 1974 eruption, and pushed lobes down into the valleys below. Seismicity is low. The ground is deflating, not inflating. There have been no explosions since May 2021. Scientists at Purdue, Carnegie, and the USGS have imaged 2 magma reservoirs beneath it and proposed a multi-stage cycle that explains why it keeps going. Nobody is currently forecasting a catastrophic explosive event, and I am not going to imply one. What is true is that this is happening under some of the busiest air routes in the world, at a volcano watched by a monitoring network that is expensive, remote, and perpetually one budget cycle from being thinner than it should be. And it is happening in near total public silence, which loops us right back to where we started. Not Kilauea, not Yellowstone, not the one that made the news. A 709-foot mountain on an empty island, quietly pouring out lava for 5 years while almost nobody watches. We will keep tracking this one. When the flow direction shifts again, when AVO changes that color code in either direction, when the next paper lands, we will cover it here. Subscribe to the channel so you do not miss it. It is completely free. And leave that comment below. Had you heard of Great Sitkin before today? Yes or no? I read them. Hit the thumbs up if this was worth your time, and let's get this one to 5,000 likes. Thanks for watching. See you in the next one.